When we are going to discuss about this chapter solutions, mainly it comes in our mind that is called liquid solutions. Here the liquid solutions can be classified into two types, that is called first one ideal solution and non-ideal solution. So these are very important properties we are going to study here. So let's take first one, that is called ideal solution. So what it is? The solution which obey Rod's law over the entire range of the concentration. So you know that what is Rod's law? That is nothing but partial of the pressure of the solution. I mean a component that must be directly proportional to the mole fraction of the component that must be present in the solution. So that is called Rod's law, right? So the solution which obey Rod's law, those we are going to call as the ideal solutions. Those which does not obey Rod's law, those we are going to call as the non-ideal solutions. Let's take an important properties of these ideal solutions one by one. Let's discuss here. So first property tells that the volume of the mixing is zero. That is called delta VT. Delta V is nothing but the change in volume. How to judge this one? Let's take an now I am going to take a solute. Right. So here solute is nothing. When we are discussing about the liquid solution, solute is nothing but the liquid, solvent is nothing but the liquid. But what about the solution? Solution is nothing but the mixture of the solute and solvent. So now I am taking this solute A and this solute as B. Right. So if I am going to take around 15 ml this volume, and also this will get 15 ml. So what is the result? I mean that is called mixture, that is called AB, right? So how much it contains? 30 ml. And I am going to add this one, solute plus solvent, I am going to get the solution, that is called 30 ml. So how do you say that is change in volume? That must be equal to 0. So now I am going to take this change in volume, that must be equal to, first what is the volume of that solution? Volume of the solution, that must be equal, that must be minus, right? You are going to subtract this one, right? Volume of the solution minus volume of the solute plus volume of the solvent. What we are going to get here? Suppose that is called change in volume. What is the volume of the solution? Volume of the solution is 30 ml minus volume of the solute, that is called 15 plus 15. So what about this answer? Delta V is equal to 0. That is called change in volume. That is so the solutions which obey this rule. So let's take a second property that tells that the enthalpy of mixing of the pure components to form the solution, that must be equal to 0. That is delta H is equal to 0. What is this delta H? Delta is nothing but the change in enthalpy. So now I am going to take a solute once again, that is called A molecular interactions. A molecular interaction plus B molecular interactions. So finally I am going to get as 2AB, right? When you are going to mixing this solute plus solvent, we are going to get the solution. Here, so in order to break down this bond, we require some energy, right? So if I am going to take around 100 energy, if I require to break down this bond, and also here also I am taking 100 energy. So what about this? 2 times of this AB is nothing but the 2 into 100 times of energy, right? That is called 200. So when I am going to calculate this change in the enthalpy, that is delta H is equal to, what is what? Enthalpy of the solution, right? First I take the enthalpy of the solution minus, I am going to subtract this one, reactant. Enthalpy of the solute plus enthalpy of the solvent. So what I am going to get here? That is change in enthalpy equal to, what is the enthalpy of the solution? How much energy is required? That is 2 into 100, that is called 200 energy minus, what is the enthalpy? How much energy is required to break down this bond? That is A molecular interaction, that requires 100 plus this is also required 100. What about this when you are going to calculate this one? That is nothing but the delta H is equal to 0, because this is 200 minus 200, that cancels 0. So that is called enthalpy, that is called change in enthalpy, that must be equal to 0. So those solutions we are going to call as the ideal solutions. Let's see the third property. Third property tells that this is a solute particles, right? A molecular interaction is nothing but the solute interaction and solvent molecular interaction. That must be attraction, that must be equal to the AB, that is called solute and solvent. Those are equal. So if I am going to take this one as the right molecules, This is called aa molecules. This is called solute molecules. Plus I am going to take here solvent molecules. That is a. This is called b. So this is attraction that must be equal to solute and solvent. That is called AB attraction. So the intermolecular attractions of these solute and intermolecular attractions of these solvent, that must be equal to the intermolecular attraction of the solution. So that is called the ideal solution. And also one more last one, that is called pressure. The theoretical pressure, that must be equal to the observed pressure. That is nothing but you know that when you are going to discuss about the Rod's law, that is called total pressure, that must be equal to PA plus B, right? Partial pressure of the component A and component B, that is equal to, for PA, that is called P naught A into XA plus P naught B into XB, and that theoretical pressure, that must be equal to the P observed, that is called observed pressures. So according to the experiment, they are going to tell that, so the theoretical pressure, that must be equal to this observed one. Let's take an example for these ideal solutions. That is nothing but the benzene and toluene mixtures. Benzene and toluene mixtures. So this is called toluene and this is called benzene. So right, here solute is nothing but the liquid and solvent is nothing but the liquid also, because we are going to discuss about the liquid solution. And also one more example, that is called N-hexane and N-heptane. So these solutions which comes under the ideal solutions. So these are the important properties of the ideal solution. Let us discuss about the non-ideal solutions. Obviously, the non-ideal solution is nothing but the which do not obey the Rod's law over the entire range of the concentration. We are going to call the non-ideal solution. And you know that in ideal solution, the theoretical pressure, that must be equal to the observed pressure, right? So here that is called ideal solution. In this case, what happens? The theoretical pressure, that is not equal to the observed pressure. So that times two categories will arise here. The first one category, that tells that the observed pressure, that must be greater than the theoretical pressure. That is called positive deviation. And second one, the observed pressure, that must be lesser than the theoretical pressure, that we are going to call as the negative deviation. So like this, non-ideal solutions can be further classified as the positive deviation and negative deviation. Let us study about this one, how we are going to explain about these pictures, that is going to be explained by the Rod's law. Right, you know that Rod's law once again. So the partial vapor pressure of the component in the solution at a given temperature, that must be equal to the product of the vapor pressure of the pure component and mole fraction. Or we can tell that the partial vapor pressure of the component in a solution, that must be directly proportional to the mole fraction. Right. So here, by looking this picture, we have already discussed about the Rod's law, right? So we are studying already these components, how we are going to write these formulas, everything. So that is called, this is total pressure, right? That is called PT, total pressure, which is going to be exerted by these pure components of this A and B. So this is partial. This is called partial vapor pressure, and this is called vapor pressure of the component A and B. So obviously you know this one, why it is in the lower form, why it is in the upper form. Because of here, this condition tells that PB, that must be greater than PA here, like this. So this is tells about the Rod's law. What about the positive deviation? What happens there? This is called vapor pressure, right? So this indicates the vapor pressure of the total vapor pressure of the component, and here only vapor pressure of the component A, and this is the vapor pressure of the component B. So this is Rod's law. By looking at this Rod's law, how we are going to judge here, how we are going to tell that this observed pressure will be greater. So let's discuss here. So this is also same diagram here, that is called vapor pressure, that must be proportional to x-axis, right? This is an x-axis, y-axis. Here this is called mole fraction, this is called partial pressure. So it tells that in this case, in this positive deviation, this vapor pressure is like this will be there, but whereas in this case, the vapor pressure of this total pressure, that must be higher than the Rod's law. This is a Rod's law. By looking this one, we are going to study the positive deviation. Positive is higher than this. This vapor pressure of the solution will be higher in positive deviation. So like this is called total pressure. Come to the components. So this is called pure component A. Here also vapor pressure of the pure component is higher than the Rod's law, and here the vapor pressure of the component B, it is also higher than this Rod's law. So this is called positive deviation. Come to the negative deviation. Negative deviation is lesser than Rod's law. Right, like this. Vapor pressure, total vapor pressure of the solution, that must be lesser than the Rod's law. We are going to write the below this curve, right? This is in curve, below curve, and also compare the components A and B. So this A and B vapor pressure also lower than this one Rod's law. This is positive deviation and negative deviation. Why it happens? Because of the solutions. That solution I am going to give the example for this one as ethanol, C2H5OH plus water. So these solutions, what happens here? Boiling point decreases and vapor pressure goes on increases. So this is case. This is called vapor pressure, right? So vapor pressure is here higher here compared to this Rod's law. Why? Because the boiling point goes on decreases. When you are going to add the mixing of this ethanol and water, what happens? Boiling point automatically reduces and vapor pressure directly increases. Like this. Why? Because these molecules are hit with each other, are repel with each other. So what about this one? I am going to take an example for this one as the acetone, CH3, and chloroform. What happens? In this case, when you look at this one, vapor pressure is decreases, right? So that is vapor pressure decreases, but what happens here? Boiling point increases. Vice versa of this one. Here boiling point decreases, here boiling point increases, vapor pressure increases here, vapor pressure decreases here. So because of these molecules, this acetone and chloroform. Why? Because they are love with each other, they are like each other, right? So they are attracted with each other. That's why this type of deviation, which is going to be exhibited in this negative deviation as well as the positive deviation. Let's study some more differences between this positive deviation and negative deviation. So let's take some difference between here. So here the force of attraction is weaker than this ieal molecular attraction and BB. So let's take here I am going to take a container that is called molecules, right? So this is called ieal type molecule and this is called BB molecules. The force of attraction is weaker than here. So now I am going to take this is this is dark one is BB and this will be ieal interaction. So after mixing, what happens? That becomes AB, right? That becomes AB. So that becomes this is A and B. So you know that when they after the mixing, like example ethanol and water, what happens? They are going to repel with each other, right? So when they repel with each other, there is no attraction between them, right? So that's why the force of attraction in this AB interaction after the product you can sell or after the mixing, this AB interaction will be very much weaker than this ieal interaction. This is ieal interaction and in BB interaction, because that's why the vapor pressure immediately increases than the Rod's law. What about this one? Intermolecular force of attraction in AB is more as compared to this ieal and BB. Same I am going to take here. This is an ieal, right? This is an ieal. This is also an BB. So when I am going to mixing these one, now they become the bond very tightly with each other. That's why they are going to attract with each other. They are going to attracting. So that's why the vapor pressure of the solution automatically decreases, because they are attracting with each other, right? They are tightly with each other because of this force of attraction. Right? You can take this one. You can do the example as a chloroform. Right? Here I am going to do the chloroform acetone, and also you can take the HCl plus water, right? So you know when I write water means there must be hydrogen bonding will be there, right? So this hydrogen bonding causes this one very stronger attraction here. The intermolecular force of attraction in AB after the mixing, that must be more as compared to this AA and BB. So because that's why vapor pressure decreases but boiling point increases. And now let's discuss a third point, that is next one, mixing. Right? Delta V, that must be greater than 0, and here delta V is less than 0. Why here the volume automatically increases but whereas here volume decreases? Because of the same reason, right? So this is when I take this AA interaction and BB, what happens? They are going to repel with each other. They are not going to attract you. If they are not going to attract this, it consumes more volume. It consumes more volume. But what about here? When they attract with each other, the volume will be automatically decreases, right? So that's why the volume of the solution minus volume of the solute plus volume of the solvent here. So what happens? That must data volume will be greater than the 0. This obviously this volume of the solution goes on increases, right? Because of this one, they are going to repel with each other. So here, vice versa, they are attracting with each other. That's why it consumes less volume, and that's why delta V, that is for change in volume, that must be lesser than 0. Let's take a fourth one, that is for change in enthalpy. That must be comes positive values for this positive deviation, and here that comes the negative values for this negative deviation. Why? Because if I take the molecules, so I am going to require 100 times energy, right, to break down this bond, and also I am taking this BP molecular interaction also 100 times energy. In order to get this bond, I am going to require only 120 energy. That is for 2 times of this AB, right? So this requires more energy to break down this bond here compared to this product one. This reactant contains more energy is required to break down this bond, but what of this product? It requires only lesser bond. Why? Because this bond is already weaker than this one, right? So because we discussed about this one, the force of attraction is weaker in AB is weaker than this AA and BP. So that's why it's equal. When you add this one, that becomes 200. Reactants minus product energy, that is called 120, right? 200 minus 120 total. I mean, for formation of this AB, it requires 60 energy. For 2 times, it requires 120, right? Total 120. This is 200 energy minus 120. You are going to get the value 80. That is called positive value, right? That's why here the enthalpy, change in enthalpy, that must be comes under the positive values. What about this one? Let's take same A molecular interaction plus BP molecular interaction. We are going to obtain this AB. So whatever it does, the intermolecular force of attraction in AB is more as compared to this AA. Suppose same, I am going to take this 100 energy. This is also 100 energy. So here it requires around 240. I can tell 240 energy. That is called this AB requires 120, and 2 times of AB, that becomes 240. Why this happens? Because first let's solve this one. So that is called 200. This is the reactant minus product energy 240. What about this answer? That comes the negative value minus 40. That is called delta. That is delta H, change in enthalpy, that must be lesser than this 0. What makes this one? Because of this hydrogen bond, like this. So now I am going to reduce. This is called acetone, right? This is acetone plus chloroform. I am going to take here. Chloroform formula is CHCl3, CHCl3. So here what happens between this acetone and this chloroform, that is called AB interaction here. What makes this oxygen and hydrogen? Because this oxygen is electronegative, right? So this is the hydrogen. This forms the hydrogen bonding in this molecule. That's why this AB attraction will be more here. That's why in order to break down this bond, it consumes more energy. So that's why here we are going to get the value as the negative values for this one, right? So this is the very important difference between this positive deviation as well as the negative deviation.